What's up guys, Major Math with another video on fluid mechanics. If you have any questions, drop it in the comments, and if you're having trouble with other problems, I've attached my email in the description, so please feel free to reach out. Without further ado, let's get started. Okay, question 1.26 in the textbook. Calculate the number of molecules in 1 cubic centimeter of liquid water at room conditions and 1 cubic centimeter of air at room conditions. Okay, so first step, as always, write down our goal. Find number of molecules in 1 cubic centimeter of water and air at room conditions. All right. We're given volume equals 1 cubic centimeter. It's basically all we're given, and we're also given that it's at room condition. So we're going to assume that room condition means pressure equals just standard atmospheric pressure, and that temperature equals 20 degrees Celsius. I'm just going to assume that's what that means. Okay, so you might be wondering, how do you find the amount of molecules? So, I don't know if you remember from chemistry, but you need to find the number of moles, right? You need to find N. That's an N. So you need to find the number of moles, and then once you do that, you can multiply Avogadro's number. Don't know how to spell it. Avogadro's number to get your number of molecules. Okay. So when we're looking at water and looking at air, we gotta find the amount of moles. Let's do water first. So now we gotta think of equations that this moles, the amount of moles this N is involved in, what equations? So if we pull out our table here, we see that looking at these ideal gas law equations, you can use a number of these. We got an N there. We also have an N here. For the water, we're going to use this for air and this for water. Okay, just to show two different ways to do it. Okay, so we got molar mass equals mass over N, right? And then we also know the density equation is density equals mass over volume. We're given volume and we're not given density, but because of those room conditions, we can go in the textbook and see what density of water is at 20 degrees Celsius and that pressure of 1 to 18. If you go in the textbook and start looking through the tables, we'll see that the textbook says that density of water at temperature 20 degrees Celsius is equal to, I can actually show you. Table A.5 says 20 degrees Celsius, the density is 998 kilograms per meter cubed. So, and if we convert this to grams per centimeter cubed, to get that centimeter cube that we want, it will be I wrote that backwards. Huh? It should be the other way around so they cancel out. It's just the conversion rate so that these will cancel out, and then you can multiply it by 1,000. I did it again. 1 kilogram over 1,000 grams. So these will cancel out. If you put that in the calculator, you'll get 0.998 grams per cubic centimeter. So that's our density. So now we can solve for our mass, right? So we have the volume, we have our density, we can solve for the mass. And that will help because we can solve for our mass, here, once we solve for our mass, we plug in here, and we can solve for our molar mass, and we can find that in. So that's the whole point, reason why I'm doing this. Okay, so we got our volume is 1 centimeter cubed, and our density is 0.98 grams per. Okay, and that, of course, is just grams. These cancel out. That's our mass. Okay, so we figured out our mass. Now we gotta figure out our molar mass, right? I'll go ahead and rearrange this. We have our mass, now we gotta find our molar mass. So, to find for water, we know that the chemical formula for water is H2O, right? So we got 2 hydrogen and 1 oxygen, right? If you look on the periodic table, we know that the weight of 1 hydrogen molecule is 1.01 grams. We know that the weight of 1 oxygen molecule is 16. Right. We have 2 of those, so we got to multiply by 2, multiply this by 1. So we get 2.02 grams, 16.0 grams. We got to add these together. We get 18.02 grams, and then this will be our molar mass. So for 1 mole of a H2O, so a water molecule, will be 18.202 grams for each mole. So that's our molar mass. That's how we solve for that. So now we have our mass, or our molar mass. Now we can find our number of moles. And like I said, once we find the number of moles, multiply by Avogadro's number, we get the number of molecules. So that will be, what's our mass? 0.998 grams, 18.02 grams per mole. These will cancel, and this will go on top, and that will give us 3.33 times 22 moles, right? Now that we have this number, multiply by Avogadro's number, which is, let's see, it's like 6 point something, 6.022, yeah, 6.022. You can just get this from your textbook or online. Sorry, this is getting crowded. Hopefully you guys can see what I'm doing here. Let's separate that. So if you multiply those out together, you will get, so this was actually the final answer. I looked at my notes wrong. So, actually, if you do this, that makes a lot more sense, actually. So this calculation is actually supposed to be 4.2 times 10 to the negative 4 moles. And then if you multiply by Avogadro's number, then you will get 3.33 times 10 molecules in water. So that is the answer to the first question. Part A, that was part A. Part B is air. This one, you can't really find the molar mass because air doesn't really have a chemical formula. So we got to find another way to find those moles. So we looked at here earlier. We kind of looked at these equations where moles are involved, number of moles, and there's an equation right here. We're going to use this equation. So we got ideal gas law. You guys can see that. Density times volume equals number of moles times the universal gas constant times temperature. Okay, and we're got to be solving for the number of moles, so let's go ahead and rearrange this. Density, that's not density, is it? Is it? It's pressure. I said that wrong. Ignore what I said earlier. It's pressure. pressure and volume over universal gas constant times temperature. Okay. So we're assuming at room conditions the pressure is 1 atm, and we know that 1 atm is equivalent to this many pascals. Converting into pascals, just when you're dealing with the ideal gas law, it's really good to get it in these those standard units. So we gotta get it in the pascals. That way, everything will just cancel out nice and easily. We know that pascals are equivalent to newtons per meter squared. Okay, and then volume. We do not know volume yet. We'll get to that in a second. The universal gas constant we know is 8.314, I believe. Yep, 314 joules per mole per Kelvin. And I'll also write this as, that's newtons times meters is the same thing as joules. And I'm just doing this because when we start to calculating, it'll be easier to cancel out those units. And then temperature, it needs to be in Kelvin for the standard units of the ideal gas law. So we're given that's 20 degrees Celsius, or that's what we're assuming. And then we're going to go ahead and add the conversion rate to give us Kelvins. Okay, and then to solve for volume, oh my gosh, we don't have to solve for volume. We're given volume. Okay, we're given volume too. Right. Okay. So we're going to need to convert this as well. Let's go ahead and just do that now. We're going to put it in meters cubed to get in the standard units. So that will be like that. We'll just plug, when we do it, we'll just plug in this number right here. Okay, so then now we have all our numbers. Let's go ahead and plug in. We'll do a little plug and chug. Volumes. And then we got right, and that is time, multiply that by temperature, is 293 point, oh, yeah, I did that right, yeah. 293.15. Okay, I see that our units really cancel out well here. We'll just be left with these moles. These will cancel. Yeah, so then we'll be left with 4.157. Okay, so that's where n is. And so we know that if we multiply this by Avogadro's number, we will get, so you guys haven't been being able to see that. Okay, so all I did is I took these knowns and I plugged it into this equation right here and just plugged and chugged. That's all I did. See, these units cancel out. Then we get this. Now that we have the number of moles, we can multiply by Avogadro's number, and that is 6.022 times 10, and that will give us 2.5 times 10 power of 19 molecules in the air. There you go. Thanks for watching, soldiers. Don't forget to leave a like and subscribe for more content like this. If you have any questions, leave it in the comments, and if you need help with any other problems, feel free to contact me with the email shown on the screen.